Hello everyone, welcome to course, and in this particular topic we are going to discuss spatial filtering techniques. And there are two types of filtering techniques which we incorporate in digital image processing of remote sensing data. One based on the spatial filter and another one is based on the frequency, which we will discuss in the next lecture. So first we will go through this spatial frequency and spectral frequency. So first spatial frequency, that is the radical variation in grayscales like here. So we consider as a high frequency image, but if we go for images, sometimes we get the images which are having low frequency. That means basically a high frequency and low frequency images. That means that basically the variations in the pixel values, adjacent pixel values is high in case of high frequency image, and in case of a low frequency image, that variation among two adjacent pixels is not that great. So the neighborhood plays very important role, and the spatial filters are also designed accordingly to enhance the images so that the image quality improves for better interpretation. So in this high frequency image, this is rough textured areas of an image where the changes in tone are abrupt over a small area, have a high spatial frequency. Whereas in case of low frequency, it appears as very smooth area with little variation in tone over several pixels, have low spatial frequency. Sometimes in the images we would like to highlight the features which are more regional in character than the features which are in local in character. So when we go for the features which are regional in character, we go for low frequency filtering techniques, and when we want to highlight the local features, then we go for high frequency filtering techniques. So that we will also see here, that if we do the changes, then these might be the results in that one. So spatial frequencies, how can we define, is that the number of changes in the brightness values per unit distance for any particular part of the image, because these spatial filters are maybe 3 by 3 pixels, 5 by 5 pixels, 7 by 7 pixels. These numbers have to be the odd number, because the center pixel is the target pixel for which the new pixel value is calculated. So in this case, in case of, as I have mentioned, the low frequency details, few changes in brightness values over a given area. That area looks very smooth, images looks very smooth, but regional features can be picked up very easily in the images which are having low frequency details. And contrary to this, high frequency images or the details, the brightness value changes and dramatically, abruptly over a short distance, and they create high frequency details. Now in this spatial filtering techniques is a local operation, and also called the convolution filtering technique. Low pass filter emphasizes regional spatial trends, and at the same time it de-emphasizes the local variation. So high frequency features are reduced, and whereas low frequency features are enhanced or emphasized, and that's the purpose of low pass filter. Whereas in case of high pass filter, it would do the just opposite as to low pass filter, whereas it will highlight the local features, local spatial variability, and will reduce the regional spatial variability. And there are some other types of spatial filtering techniques which are also called edge enhancement techniques, which combines both filters, that means low pass and high pass, and to sharpen the edges in the image. So wherever the boundaries of different features are present in the image, those boundaries are sharpened, and therefore maybe in some cases a better interpretation. See, this one thing one has to remember, that a single technique every or let me put like this, that every technique is not suitable for every kind of images. It depends on what is the spatial resolution of that image and what is the purpose, ultimate goal of creating a digital image processing image so that we can make the better interpretation. So there is no universal technique or a flow of processing that this has to be applied on every images. If this would have been, then a simple automatic system would have been generated. Even if some is working on one area but on different seasons images, then probably one has to employ different image processing techniques to enhance that image, or those images of belongs to different season of the same area. So there is no straightforward in that, say that every time you have to apply this. It depends on the image, what is the contrast, what is the features, and how they are presented in association. So like the first example here is having zero spatial frequency, no variations among pixels, and a flat image in which every pixel has the same value. It may happen where you are having a completely snow covered areas of a flat terrain, or maybe a desert area where it is completely featureless terrain. And low spatial frequency, an image consisting of a smoothly varying grayscale. So very gently the pixel values are varying, and highest spatial frequency example is already here. Now in filtering, what we do basically, if we consider a 3x3 filter, then it is moved throughout the image, and for the center pixel a value is created, a new value is assigned. That value will come on the weights we assign to the spatial filter. That we will see here, that in spatial filtering, the process of dividing the image into constituents of spatial frequencies and selectively altering certain spatial frequencies to emphasize some image features, and this process of suppressing, that is de-emphasizing certain frequencies and passing certain frequencies, and this technique increases the analyst ability to discriminate details. Ultimately, we are trying to improve the image quality for better interpretation for all techniques. Local operation, this is local operation because it has to be performed one by one on each pixel except the pixels which are present on the edges of an image. So if you are having a 3x3 pixel spatial filter, then one pixel on all sides will not be involved in the analysis. But if you are having a 5x5 filter, then 2 pixels on all sides of the image will not be involved. So local operations it is, and the pixel value is modified based on the value surrounding it. The surrounding value will decide what should be the value here, and used for enhancing certain features. Also can be used to remove noise, like speckles. Sometimes we are having a noise in the images. In previous lectures I have shown some images, so that speckle thing can also be removed by filtering. And smoothing of image, sometimes there are a lot of variations, means high frequency features are present. I want a smooth image appearance so that I can look the regional features, so that can also be achieved. Here is the example that where the low and high frequency features are there. Here see this, it is having very high frequency features, whereas in at different places you are having low frequency features. This is part of our Shivaliks near Haridwar. And now here these are the how filters are designed. So we will see one by one. That algorithms for filtering that is composed of a window mask or kernel, convolution mask or moving matrix of 3x3, like mask size is mentioned here 5x5, it has to be an odd number. In this one all these values are being, so the weight for all pixel values is same, but we can have a different. So this becomes a square mask if we involve 3x3, 5x5. Now the convolution filtering technique, the process be defined, the process of evaluating the weighted neighboring pixel values located in a particular spatial pattern around the ij location in the input image. And the technique is this mask, this roving window, the convolution filter will move over each pixel, will take the values of surrounding pixels depending on the weight which has been assigned to individual cells of this mask. The new value is calculated and mask window is placed over part of image. Convolution formula is applied over the part of image, that is the sum of weighted product is obtained. Coefficient of mask x row, that is the digital value divided by sum of coefficients, and the central value replaced by the output value. And the window is shifted by 1 pixel and procedure is repeated for the entire image. So, one pixel by pixel this process will be done. Here is the example that this is the input image and this is the filter. Now, step 1 is to place over the part of the image. So, this will go over this image and one by one it will keep moving, but at the same time it will calculate a new pixel value for the central pixel over which this would be placed. So, here this is now placed here, and now this is how the value will be calculated. So, for the central pixel, that is the C5, the value is calculated, and depending on the weight which you have been assigned, this formula will be applied. So, likewise for this central pixel, then step 3 it will move for the next pixel, and likewise. So, now it has the C5, that means for this pixel, and now again filter has moved one step right side and new value has been calculated, then again shifting, and likewise keep doing for entire image till it reaches to the end of image. But as I have mentioned, if you are using a 3 by 3 spatial filter, convolution filter, then 1 pixel on the edges will not be considered, because there is, and this filter cannot go on the first pixel at first row. It has to be done on second pixel of first row of and second of second column and second row. So, first column and first row pixel cannot be done for the all corners and on the sides as well. And likewise it goes till the end, and the last pixel is for last pixel it is calculated. So, using 3 by 3 kernel results in output image, 2 lines and 2 columns is smaller. The boundary pixels are either copied from original image or duplicated from side then computed. Here is the example is given here, and that this is the input image, the pixel values are given here, and this is the filter, low pass filter has been applied. So, it will use a weighted average, sum of these all values, weighted average, and that value will be assigned to the central pixel over here. So, like in this case, when we go for this run filter, then this is what we see. See, on the edges there is no change, but we will see that on the other part the things will change. So, now this filter is here and it is calculating new value for pixel 80, and likewise this value becomes 63, and likewise the next one, and then at the end you come here. On the edges 1 pixel by 1, this has not been considered, but remaining values have changed. So, the 55 first row is the same, but the second row, second pixel has changed. Instead of now 80, it has become 63, and 69, 70, 64. Now, the variations which we are present here between these pixels have reduced, and therefore the high frequency features have reduced and low frequency features have been emphasized by doing this kind of filtering. And this is how the calculation is done. Then when it goes, so 76 has been calculated, considered 72, and because depending on the weight, 76 multiply by 1, and then we go for all these pixels one by one. That sum of all this is 577, it is divided by 9 because it's a 3 by 3 filter, you get a output value 64, which is assigned there, here. So likewise you see the process, and the gray values are also given here. You can for the entire image it is done. So this last image example is shown here. This is 64, and this is of course a linear stretched image or not image that can also be seen. In real image, this is how it. So this low pass filter has been used here. Two different examples are given. This is how the calculation done. On the edges nothing is done, and these are the results. So since this is a low pass filter, and therefore this high frequency features have been de-emphasized, whereas low frequency features have been highlighted, and this is what you are see in the result image, which is a low pass. Either 1 by 9 you can change, or 1 by 1 you can assign the weight. The result is same, because here multiply by 119, and we end up with this image. So you can compare that what happens to the pixel value. They become very close to each other, and therefore the local variations reduces, de-emphasized, and the regional variations are emphasized. Central pixel becomes very important. So here the central pixel value is shown here, is 201, and after the calculations it might be 186. And before filtering this was the situation, and after filtering in case of high pass filter, this is how the local variations then would be highlighted in high pass filter. So low pass filters will block high frequency details or de-emphasize high frequency details, has a smoothing effect on images, used for removal of noise, removal of salt and pepper noise. Salt and pepper means that every alternate pixel is having a very sparkle kind of thing. One is dark, one is light, one is dark, light. So that is why it is called salt and pepper, and blurring of image, especially at the edges. So this definitely will create one pixel problem on the edges of the image. High pass filters preserves high frequencies, remove slowly varying components, that means low frequency things, emphasizes fine details, used for edge detection and enhancement, and edges locations where transition from one category to another. Now this is the example of shown here, that if this is the original image, this image have gone subjected to a 3 by 3 filter. This is example of 7 by 7 filter, and this is of 9 by 9. And this is how the filters, as the matrix or the filter becomes larger, that means it is averaging the pixel values larger from the surrounding. So more areas are involved to calculate a pixel value for a target pixel or center pixel, and therefore it will reduce the local variations very significantly, as you can compare between 3 by 3 filtered image and 9 by 9 filtered image. One more thing one has to remember: larger the size of the filter, more the time it would take in the processing. So if you are having large image, initially one should go for 3 by 3 and see whether you are achieving the results which you wanted to have. Then if not, then go for 7 by or 5 by 5, then maybe 7, because size, if you increase the size, and the processing time would increase exponentially. So this one has to remember. This is another example of median, that was the mean filter, different variations of low pass filter. This is median filters is there, and it is de-emphasizing the local variations and emphasizing the regional very clearly. Now this is mode filter. So there is another changes are there, and for the same image which you have taken. In case of high pass filters, we can take linear or non-linear. The output brightness values in case of linear is a function of linear combination of brightness values located in a particular spatial pattern around the pixel ij location in the input image. And in case of nonlinear, use nonlinear combinations of pixels. So these are used, high pass filter used to emphasize the local variations, maybe edge detection, and the background is lost. Edge enhancements, very popular technique that delineates edges and makes the sharpness and details more prominent, and background is not lost. So edge enhancement, edge detection, edge enhancement, this is the example here, that now we are having a high pass filter, and the center pixel will have very high weight in this 3 by 3 matrix, and whereas surrounding pixels it is a minus value, and the result you would see when we go one by one, that see that the first value now we are going to change, it will become 98. So instead of 80 it becomes 98, and likewise for entire image when it is done, except for the one pixel on the edges, these values have changed significantly. The difference between these two adjacent pixel values has changed significantly. Earlier they were difference of just 15 pixel value, that means 80 and 95, now it is 98 and 123. So 25 instead of 15 difference, now we are having difference of 25, and therefore the local variations have been highlighted. If we give some directional touch to this filter, then in that particular direction where your features are present, they would be highlighted. So a high pass filter can also be modified to make a directional filter, which we will see just later. So this is the gray image, and this is what you are seeing, the enhancement in them. That means enhancement in the sense that the local variations have been highlighted very significantly just using a high pass 3 by 3 filter. And this is high pass filter, and the convolution matrix, the filter size is very large, and therefore all regional variations have disappeared almost, and you are seeing just the edges of different features, and all these things have been highlighted very clearly here. Edge detection, that is the zero sum kernels, and in zero sum kernels in which the sum of all coefficients in kernel equals 0, and this generally causes the output values to be 0 in areas where all input values are equal, no edges, low in areas of low frequency, and extreme in areas of high spatial frequency. Therefore, this zero sum kernel is an edge detector, which usually smoothen out or zero out the areas of low frequency and creates a sharp. That means the all regional variations will disappear, only these will come. And an example of this edge detection filter may be like this, that you are having only in the top part you are having the minus values, whereas here you are having positive value, and the center value is having -2, and this is a 3 by 3 filter example. And therefore one can design several filters, as I have been mentioning. This is one type of spatial filter, high pass filter, which we have seen. This is another, and there are few more examples are there. So here this A is the original image by devising matrix based on the more complex algorithms, that is B and C, where we have changed, and instead of involving -1 all surrounding pixels in the filter, only north, south, east, west have been involved, north, east, south, west have become 0. Edge enhancement matrix results from adding the edge detection of the original image. Here now edge has been added, so here -2, 4 and -2, this is creating, and the features which are present in east west will be highlighted, features present in different directions will be highlighted, and likewise you see that results are there. And now these are examples of the almost same area, the original image, 3 by 3 edge detection. So only the features which has the sharp edges have been highlighted, rest completely gone in the background. So if somebody is looking for such outputs, to delineate certain things, maybe linear features or features which are having sharp boundaries with surroundings, such filters can be adopted. And if I go for 5x5 edge detection, I may get image something like this. So like if I take this example of A will produce image in northwest direction, this is directional filter. So in northwest direction, and whereas a B in a southwest direction. So this is a southwest direction filtering, and this is how the result would be. The directional filtering will highlight in a particular direction the way the filter had been designed. So here from different directions tend to enhance or disclose linear features that lie preferentially near the perpendicular to the transverse directions. In the image below, the array was moved diagonally across the scene. So entire pixel this has been moved, and as you can see that these features which are linear one or the boundaries have been highlighted very significantly in the direction, in a particular direction. Now there are different, once the concept was introduced about spatial filtering, then there is no sort of limit, and one can keep involving few more permutation or combinations within 3x3 or 5x5. So there is an example of Laplace edge detectors, Laplace edge enhancement filters, and different weightages are assigned to different cell values of factor. This is nonlinear edge enhancement using the Sobel operator. So this kind of calculation can be performed. One of the output is like this. This is the original image. After through Sobel filter, this image becomes something like this, and like here features are much more highlighted, edges are much more clear as compared to original image. So there are various such filters exist. One can also design its own filter as per requirements and can use them in digital image processing softwares. So this is an example of Roberts as filter, and this therefore I would like to mention here that as I mentioned also earlier, that there is no standard filter which one has to apply on each image. Depending on the image type, the features which are present in the image and your requirement, one would apply a filter. So if I am looking for regional features, then I will go for low pass filter and will try to enhance the regional features. Whereas if I am going for looking for local variations in the pixel values and I would like to highlight further, then I will go for high pass filter. A variety of high pass filter is directional filter. These are very useful. If you are looking the features which are particularly in a direction, then accordingly filter can be designed. These values can be all digital image, standard digital image processing softwares will allow you to design your own filter or already designed filters like Robert, Sobel, and simple generic form of filters, high pass, low pass, edge detection, and edge enhancement filters. So this brings to the end of this discussion. Thank you very much.